Now in this lesson we will learn about correlation between two variables, random variables, and orthogonality. The correlation of x and y is Rx comma y is equal to Exy, means the expected value between the product of x and y. And random variables x and y are orthogonal if the expected value of x into y is equal to 0. Random variable x and y are uncorrelated if covariance x comma y is equal to 0. So orthogonality is different from uncorrelation. Two random variables are called uncorrelated if covariance is equal to 0, but if expected value of between the two random variables is 0, then they are orthogonal. Rho is the correlation coefficient of two random variables x and y. So rho is equal to covariance divided by standard deviation of x multiplied by standard deviation of y. Rho is a dimensionless quantity and is bounded by -1 and 1. Rho describes the information we gain about y by observing x. For example, a positive correlation coefficient, rho greater than 0, suggests that when x is high relative to its expected value, y also tends to be high, and x is low, y is likely to be low. So if the uh, value of random variable x is high relative to its expected value, then y should also be or tends to be high uh, compared to its expected value. So we can say that it is directly proportional. X and y are directly proportional. However, if a negative correlation coefficient rho is less than 0, then a high value of x is likely to be accompanied by a low value of y, and that a low value of x is likely to be accompanied by high value of y. It means that when correlation coefficient is negative, then it is inversely proportional. Means that if x is high relative to its expected value, then the value of y tends to be low compared to it relative to its expected value, and vice versa. So we can say that uh, positive correlation coefficient indicates direct proportionality between x and y random variables, and negative correlation coefficient indicates inverse proportionality between x and y random variables. So if x and y are random variables such that y is equal to ax plus b, which is a straight line, then if correlation coefficient is equal to -1, then a is less than 0. Rho is equal to 0 when a is equal to 0, and rho is equal to 1 uh, when a is greater than 0. We try to understand correlation coefficient rho with some examples. First example is that x is the height of a student, means x is a random variable which indicates the uh, probability of height of a student, and y is the weight of the same student. And if in this case, the correlation coefficient rho will be positive, means its value will be greater than 0 and less than 1. The reason is that we observed that uh, most of the cases, if a person is tall, then his or her weight is high, and if a person is short, then the weight is also low. So we may say that the weight of a person tends to vary according to the height of a person. In another example, x is the distance of a cellular phone from the nearest base station, and y is the power of the received signal at the cellular phone. In this case, correlation coefficient rho is greater than -1 but less than 0, means it is negative. And this is very easy to understand for a telecommunication student, as the transmitters move away from the receiver, the signal strength drops. So in this case, for example, the cellular phone is transmitting a signal, is communicating with the base station, and the base station is the receiver. In that case, the base station, the signal received at the base station will go down, will drop, which is strength will go down, as the transmitter means cellular phone will move away from the base station. There is another example where X is the temperature of a resistor measured in degrees Celsius, and Y is the temperature of the same resistor measured in degrees Kelvin. Here, this correlation coefficient is equal to 1 because we are measuring the temperature of the same object at the same time. Only the difference is the temperature is measured in different units. So the correlation is equal to 1 because when you will convert, then it will always be the same. I mean, conversion will be always be the same. And suppose that X is the telephone number of a cellular phone and Y is the social security number of the phone's owner, then the correlation between the two is equal to 0. Of course, there is no correlation between a person's cellular phone number and his or her social security number. So in this case, the rho is equal to 0. Now we look at conditional joint PMF, probability mass function. What is PMF? First, we'll revise a little bit about PMF. We know that a PMF is a function that gives the probability distribution of a discrete random variable. For each possible value that random variable can take, the PMF assigns the probability. So, what is a PMF? It simply tells us that whatever a random variable value can take, discrete random value, at that value, what will be the probability? So, this is the PMF. And conditional probability means to measure the probability of an event happening given that another event has already occurred. Means what is the probability of event A to occur given that event B has already occurred. So the probability of event A depends on the probability of event B. We have learned about conditional probability in detail in previous lectures. One can refer those lectures if he doesn't understand conditional probability over here. So for discrete random variables x and y and an event b with probability of b is greater than 0, the conditional joint PMF of x and y given b is probability of x comma y divided by probability of b. So how do we calculate this probability of x comma y given b? Probability of x comma y divided by probability of b means the event on which it depends. The conditional variance of random variable w is equal to g of x comma y is given as expected value of w minus mu square given b. So conditional joint PMF example. Now we look at an example. Suppose random variables x and y have the joint PMF as shown. As shown means given as in this figure over here. The probabilities are given at different random variable values of x and y. Let B denote the event x plus y is less than equal to 4. Here, the event we want to observe is that what is the probability if x plus y is less than equal to 4. If we add these joint probabilities x and y, then and its value is less than equal to 4, then at that what will be the probability? So find the conditional PMF of x and y given b. First of all, we will go through this figure over here. What it tells us that if the value of x, this x is 1, and the value of this y is also 1. So at that moment, the probability of x comma y is equal to 1 by 4. If the value of x is 2 and value of y is also 2, then it is 1 by 8. If the value of x is 4, value of y is 3, then it is 1 by 16 and so on. So this only tells us that what are the probabilities at different random variable values. We can see that there is no probability given at 1, 2 and 1, 3 and 1, 4 and so on. So first of all, we have to find x plus y, which is according to this given. What are the, so why do we have to add these values? To know that which combination of x and y we have to consider. Why? Because we have got 1 comma 1, 2 comma 2, 3 comma 2, and so on. But we have to select only those random variable joint probabilities which satisfy this condition, x plus y less than equal to 4. So first of all, for example, we add 1 comma 1. It satisfies this condition, x is 1, y is 1. So 1 comma 1 is valid. 2 comma 1, 2 plus 1 is equal to 3. Satisfies this condition, so we can take 2 comma 1 as well. 2 comma 2, again it is 4, satisfies this condition. 3 comma 1 satisfies the condition, 3 plus 1 is equal to 4. 3 comma 2, this violates this condition. So we cannot take 3 comma 2. We cannot take 3 comma 2, 3 comma 3. So we will take only 1, 2, and 3. And 1 comma 1, 2 comma 1, 2 comma 2, and 3 comma 1. All these four combination of x and y satisfy this condition. X plus y must be less than equal to 4. So we have got 1 comma 1, 2 comma 1, 2 comma 2, and 3 comma 1 over here. Now what we will do that to find the probability of B, event B, we simply multiply the probabilities at these given values of probability x comma y. So as we can see, when x is 1, y is 1, the probability is 1 by 4. So we will take 1 by 4. 2 comma 1 gives us 1 by 8. 2 comma 2 is again 1 by 8. And 3 comma 1 is 1 by 12. So we will add 1 by 4, 1 by 8, 1 by 8, and 1 by 12. And what we get is 7 by 12. So this is the probability of B. That what is the probability of event B, and what is the how event B is defined? That x plus y must be less than equal to 4. So for this event to occur, the probability is 7 by 12. Next, what we do is that we use this equation over here. We'll divide. We'll have found this one, probability of B. Now what we will do, we'll find these values, probability of x comma y, and divide it by probability of B. So probability of x comma y, 1 comma 1 is 1 by 4, as we have seen before. This is 1 by 4. So this 1 by 4 is divided by 7 by 12, which gives 3 by 7. And 2 comma 1 is 1 by 8. So 1 by 8 is divided by 7 by 12, which gives after simplification 3 by 14. And again 1 by 8 is divided by 7 by 12 will produce the same result, 3 by 14. And 3 comma 1 gives 1 by 12 divided by 7 by 12. As you can see, 1 by 12 is over here. Divided by 7 by 12 gives 1 by 7. So now we have found the probability of x comma y given B. We have plotted on this graph over here as well. 1 comma 1 is 3 by 7, 2 comma 1 is 3 by 14, 2 comma 2 is 3 by 14, and 3 comma 1 is 1 by 7. Now we find the conditional expected value and the conditional variance of W is equal to x plus y. Here we have found this probability of x given B, joint probability, conditional joint probability of x comma y given B. Now we find conditional variance, W is equal to x plus y. So first we find the expected value and then we calculate W is equal to x plus y, conditional variance. So what we do is that we simply multiply these values x plus y, 2, 3, 4, and 4 by their respective probabilities, conditional joint probabilities. 3 by 7, 3 by 14. So 2 is multiplied by 3 by 7, 3 is multiplied by 3 by 14, 4 is multiplied by 3 by 14, and 4 is multiplied by 1 by 7, as it is shown over here in this column. And then they are all added to get the expected value. So that to get the expected value, simply what we do is that we multiply this x plus y with this p x comma y given x comma y, and then we take sum of them. So the expected value is 41 divided by 14. Now the conditional variance is given as W given B. This is called conditional variance. Why? Because we find the variance of W given the variance of B. So that is equal to expected value of W square given B minus E W given B whole square. We have calculated this value over here, this one, E W given B expected conditional expected value. So we will just square the value of W over here, 131, which is 131, which is square of 41 divided by 14 minus 41 over 14 divided by whole square. This we have calculated over here, 41 divided by 14. We simply square it and then we subtract it from this 131 divided by 14 and we get 153 divided by 196. This is conditional variance of W given B. So far we have talked about PMF, which is for discrete random variables. Now we talk about PDF, which is for continuous random variables. For discrete random variables, we use PMF, probability mass function. But for continuous random variables, we use PDF, probability density function. So it is very much same as probability mass function. The only difference is that here we are using function f of x comma y in place of p of probability of x comma y. So how do we calculate this f of x comma y given b? We will see by an example. For example, this function is given, the value of function f x comma y is given to us as 1 by 15 when x is greater than 0, x is greater than or equal to 0 and less than equal to 5, and y is greater than or equal to 0 and y is less than or equal to 3. So the PDF of x and y, random variables x and y, is given by this block over here. You can see this rectangular shaded area. So this is 0, 1, 2, 3, y is 0 to 3, and x is 0 to 5, 0, 1, 2, 3, 4, and 5. So this whole area, this complete area, including this dark area and this light area, is PDF of x and y, random variables x and y. Now, what we have to do is that we have to find the conditional PDF of x and y given that event B is equal to x plus y is greater than or equal to 4. Here this event is similar to the previous one, but here the condition is reverse. There it was x plus y is less than or equal to 4. Here it is x plus y must be greater than 4. So we will do the same thing as we did in PMF. The condition says that when we add the random variable value of random variable x with y, it must be and or greater than or equal to 4. So 4 plus 0 is equal to 4 if the value of y is 0. So for x plus y must be greater than 4, then x is equal to 3, y is equal to 1, again it is 4, x is equal to 2, y is equal to 2, again it is equal to 4, and x is equal to 1, y is equal to 3, again it is equal to 4. So the PDF for event B is this shaded area, darker area. This lighter area does not satisfy this condition over here. B is equal to x plus y must be greater than equal to 4. This darker shaded area satisfies this given this event B. So we calculate probability of B by integrating f of x comma y over the region B. So what we have to do is that we have to integrate this function for this region only. So what we'll do, we'll apply limits, and what according to this, from this graph, this darker area, we can find the limits over here. As you can see that the value of y ranges from 0 to 3. It is straight, right? So it is 0 to 3. but value of x is 4 minus y to 5. So, for example, is y, the value of y is equal to 0, then we get lower limit 4, which is this one. This one. If we take value of y is equal to 1, then 4 minus 1 is equal to 3, which is this one. So it will be integrated from this one to here, from here to here, this value to here. Then if it is y is equal to 2, then it will be from here to here, and so on. So if we use these limits, we will integrate the function f of x comma y for this region only, darker region. Next, this integration is very simple, but I will explain it to you in case somebody is not familiar, somebody has forgotten or is not good at calculus. So I will little bit explain it to you as well. So this 1 by 15 is a constant. We do so we take it out, and then dx is integrated as x. The integral of dx is x, so we get x over here, and then we apply this inner integration first. So we always integrate the inner one first and then outer one. So in this case, inner one is dx and outer one is dy. So first of all, we will integrate with respect to x. So integral of dx is x, and then we apply the limits. How do we apply the limits? We apply the upper limit first and then the lower limit. So we will place this upper limit in place of this variable x. So 5 minus 4 minus y. 4 minus y is the lower limit of x. So 5 minus 4 minus y. After simplification, we get 1 plus y dy. We can write this 1 over 15 outside or inside, doesn't really matter. So now here we integrate 1 plus y. Integral of 1 is y again, and because when we multiply dy by this, so we get dy plus y into dy. Integral of dy is y, and integral of y is y square divided by 2. We simply add 1 in the power and divide by the same power value. So 1 plus 1 is equal to 2, and then we divide it by 2. Now again we apply the limits. First we will apply the upper limit 3, and then we will apply lower limit 0. So when we apply upper limit 3, 3 plus 3 is square over 2 minus 0. Here we have placed 0 in place of y, 0 square divided by 2. So we, after simplification, we get 1 by 2. So the probability of B is 1 by 2, means that probability of event x plus y greater than or equal to 4 is 1 by 2. Now we simply divide this function f of x comma y with this probability p of b. So 1 over 15 is divided by 1 by 2, which gives 2 by 15. So this is the probability of x comma y given b. Means if the event is x plus y must be greater than or equal to 4, then the probability of x comma y, the joint probability of x and y, is 2 by 15 for continuous random variables x and y. Now find the conditional expected value of x, w is equal to x into y, given that event b is equal to x plus y must be greater than or equal to 4. So for continuous function, the expected value EWB is equal to integral of g of x into f of x comma y given b dx into dy. And here g x comma y is given as w is equal to x into y. This is given to us. So it becomes very simple. We simply, what we have already calculated, f of x comma y given b is equal to 2 over 15 over here. This is the result we have got from previous exercise. So we will just simply multiply this one by x into y. So here we have got xy divided by 215 dx dy. Again, first we will calculate dx and then we will find dy. And 2 by 15 is multiplied by x comma y, so we can take it out as we did before. So we have to simply integrate x and y uh, with respect to dx and dy, one after the other. So first we integrate it with respect to x. When we integrate it with respect to x, then y is becomes constant. So this y, x into y, this y becomes constant. So we leave it out and we just simply integrate x over here, and integral of x is x square over 2 as we have seen before. We again apply the limits 5 and upper limit 5 and 4 minus y, the lower limit as we did before. And after simplification, now we multiply this 25 minus 16 plus 8y minus y square by y, and finally we get 9y plus 8y square minus y cube. Now we have to integrate this term with respect to y, and again we will integrate each term separately. So 9y square divided by 2, it is 9y, so integral of 9 is y square over 2. So we have got 9y square over 2. Integral of y square is y cube over 3, as we know that we have to add 1 in this power and then divide it by the same value. And then this y cube will become y's power 4 divided by 4. So this is what it is written over here, and then we apply the upper limit first and then we apply the lower limit. Rest is the simple arithmetic, and finally we get 123 by 20. Now our next topic is bivariate Gaussian random variables. The bivariate Gaussian distribution is a joint probability model for x and y with the property that x and y are each Gaussian random variables. Bivariate Gaussian random variables x and y have a bivariate Gaussian PDF with parameters mu1, sigma 1, mu 2 means this is standard deviation, this is mean, and this is correlation coefficient. So the following three figures illustrate the bivariate Gaussian PDF for mu 1 is equal to mu 2 is equal to 0, mu 1 is equal to sigma 1 is equal to sigma 2 is equal to 1, and three values of rho. Means in all these three figures, the mean value is 0 and standard deviation is 1 for both random variables x and y. But the only thing which changes is the correlation coefficient. So here is this is the first example where mu 1 and mu 2 both mean values are 0 and their standard deviation is equal to 1. And in this case, this correlation coefficient is also 0. So what we see is that we get something is shaped like a sombrero, means like a hat over here. Means you can see that this curve is not very steep, it's very low. But when rho is equal to 0.9, means it is very high, positive high value of correlation coefficient, which is equal to 9, then we see that they form a ridge over the line x is equal to y. They form a ridge like this, which is x is equal to y. And if the correlation coefficient is negative, means negative high, minus is equal to minus 0.9, then we see a ridge over the line x is equal to minus y. The ridge becomes increasingly steep as rho increases, plus minus. The only difference is that the direction of the ridge has changed over here. Otherwise, this one is similar to this one.